Hello students, welcome to APG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Reaction Part 1 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of nuclear collective model, number 2, knowledge of collective vibrational model, number 3, knowledge of collective rotational model. Nuclear reaction. In this slide, we are going to study what a nuclear reaction is and how we represent it. In nuclear reaction, one pair of nuclei becomes a pair of different nuclei. It means in the nuclear reaction, two nuclei interact, and after interaction, nuclear reaction, the two different nuclei are produced. For example, here you can see one reaction is given where nitrogen 14 is reacting with helium or alpha particle. When they two react or undergo nuclear reaction, then 17 oxygen plus proton is produced. More accurately, we can write this equation in terms of 14n bracket alpha p bracket close 17 oxygen. So this is the shorter form of writing a nuclear reaction. So now first of all, it comes to our mind that why nuclear reactions are needed, why they are so important, and what is the need of having the nuclear reactions. So in this slide, basically we will look into the issue that why the reactions are necessary. So the nuclear reactions are necessary, number 1, to produce exotic nuclei. What does that mean? If we want to produce a nuclei or a nucleus which does not occur in nature in a stable form, then nuclear reactions are the only way. To produce exotic nuclei, it's a most successful way of producing unstable nuclei is by reacting them together in various combinations. For example, if we want to produce oxygen-22, oxygen-22 doesn't exist in nature. So we choose a proper beam target combination and a proper energy for the reaction, and then when the nuclear reaction happens, then in some of the cases oxygen-22 will be produced. But since oxygen-22 is very exotic means it has got a very short half-life, so it will be produced and it will eventually decay. So oxygen-22 is produced via nuclear reaction, whereas oxygen-22 is exotic. Second important point that why do we need reactions is to explore the structure and static properties of nuclei. Suppose if we want to study the nuclear structure property of, say, oxygen-18, then in order to understand its properties, we need to excite it. We need to excite oxygen-18 so that when it decays by gamma, beta, or whatever means it will decay. We collect those radiations and then can infer the information regarding the structure of oxygen-18. So nuclear reactions basically are needed to explore the structure and static properties of nuclei. This is one of the major tools to study nuclear structure. Third important point that why do we need nuclear reaction is to probe the dynamical characteristics of nuclei and nuclear matter. For example, the study of equation of a state of nuclear matter. That is, suppose we want to study that what happens when a nucleus is basically hit by other nucleus with high energy. So what happens is, then the nucleons basically, the energy of the reaction is shared among the nucleons which are in nucleons of the nuclei which are interacting. So there basically rearrangement of the nucleons take place. So if we want to study what is happening inside the nuclei during the nuclear reaction, then that can be produced or that can be studied by having a nuclear reaction. Nuclear reaction. Now in the nuclear reaction sections, we have understood what are the nuclear reactions and what are the conditions required to have the reactions. But in this slide, we are going to study how a nuclear reaction is produced. Now, every nuclear reaction can be divided into three subcomponents. The nuclei which undergo reactions are called reactants. Once they react, then whatever is the outcome or the product, they are called products. Then the nuclear reactions can be conveniently represented in subcompact form. Then those compact forms are called representations. Now here in this case, lithium-7 nucleus is reacting with lead-208. Now depending upon how much energy and angular momentum is imparted in the system, we have variety of output products. In some cases, the reaction may lead to the production of 215 astatine plus gamma. In the other cases, we have the production of 212 astatine plus 3N. In another cases, we have the production of 197 gold plus 18 carbon, and in some cases we have fission. So 7 lithium when reacting with lead-208, it's called entrance channel, and the products we are getting, the variety of things that we are having as products, that is called an exit channel. Now if we wish to represent them compactly, then the first possibility where astatine 215 was being produced can be represented as 208 lead bracket 7 lithium comma gamma bracket close 215 astatine. In the second possibility, we can represent as 208 lead bracket 7 lithium comma 3N 212 astatine. In the third possibility, we have 208 lead 7 lithium comma 18 carbon bracket close 197 gold. And the last possibility where the fission is happening as the exit channel, we can represent it compactly as 208 lead bracket 7 lithium fission nuclear reaction conservation laws. Now in the previous slide, we have understood how the nuclear reaction is produced. In this slide, we are going to study the conditions under which the nuclear reactions happen. Whenever the nuclear reactions happen, they are basically guided by the various conservation laws, and the output also depends upon the conservation laws. What are the conservation laws that need to be satisfied? First of all, the conservation of total energy and conservation of linear momentum. These two are the fundamental conservation laws that need to be satisfied in order to have a nuclear reaction. Now, these two conservation laws will tell us how much energy we can expect in a nuclear reaction. Another important conservation law is the conservation of proton or neutron number. That is, when the two nuclei are reacting, then the total number of protons in the system and the total number of neutrons in the system must remain conserved. Next, conservation of total nucleons. It is also one of the conservation laws which need to be satisfied, that in the overall process the initial total number of nucleus, that is total number of nucleons in the entrance channel, must be equal to the total number of nucleons in the exit channel. This situation is basically observed and satisfied at high energies. Then conservation of angular momentum is other thing. Conservation of angular momentum means the conservation of spin in the reaction, that is in the entrance, and the total spin in the entrance channel must be equal to the total spin of the system in the exit channel. This is really important for spin assignment of nuclear states. And next thing is conservation of parity, that is whatever is the parity of the reactants in the entrance channel, the same should be the parity in the exit channel. Nuclear reaction energetics. In this slide we are going to study what are the energetics, or in what way and how much energy is involved in the nuclear reaction. For a given T bracket Px bracket R reaction, ignoring the electron binding energy, we have Mpc square plus Tp plus Mtc square is equal to Mrc square plus Tr plus Mxc square plus Tx, where T is the kinetic energy, M is the mass and C is the speed of light. What does this mean? That for a given reaction in which particle P is being bombarded on target T and reactant R is produced along with the emission of a light particle like X, the total energy conservation laws will give you this equation. The Q value of the reaction, Q value is also called the energy of the reaction, that total energy involved in the reaction. Q value of the reaction is defined as the difference in mass energies of the product and the reactants, that is Q is equal to Mp plus Mt minus bracket Mx plus Mr C square is equal to Tx plus Tr minus Tp. So this is basically how the Q value in the nuclear reaction is obtained. Nuclear reactions. In nuclear reactions, one pair of nuclei becomes a pair of different nuclei. So this is the way the nuclear reactions basically happen. Two nuclei, for example, in the given case, 14 nitrogen is reacting with the alpha particle, and after the nuclear reaction, oxygen 17 is produced along with one proton. So this is what happens in nuclear reaction, that two nuclei interact, they undergo nuclear reactions, and different set of nuclei are produced after the reaction. In order to write the nuclear reactions in the compact form, we can write the above equation in the form, that is 14N bracket alpha P bracket close 17 oxygen. So it gives the complete expression for nuclear reaction, that what is happening, which one is reacting with what, and what are the things that are being produced. Now the important question comes that why do we need nuclear reactions? Why they are so important? Why we are discussing them at all? There are several reasons which will tell us that why the nuclear reactions are important, and in fact in some of the cases the nuclear reactions are the only one. For example, number one, to produce exotic nuclei, we definitely need nuclear reactions to produce exotic nuclei. Exotic nuclei means which you cannot have under normal conditions. For example, if we want to produce oxygen 22, oxygen 22 doesn't exist in the nature. It is produced in nuclear reactions. So if we want to produce and study oxygen 22, then nuclear reactions are the only way. So it's a most successful way to produce unstable nuclei is by reacting them together in various combinations. So if we want to produce any exotic nuclei or any exotic nucleus, we have to we have to uh, we have to rely on the nuclear reactions. Second reason that why nuclear reactions are important is to explore the structure and static properties of nuclei. For example, if we want to study the structural properties of oxygen 18, what is structural properties? That how the neutrons and protons are arranged in various energy orbitals inside the nucleus. So, if we want to study that, we need to produce oxygen 18 in a nuclear reaction so that the oxygen 18 will be produced in the excited state. When it de-excite, it emits several gammas, betas or alphas, whatever the case may be, and then we trap those radiations, and then by analyzing what we have got, we can infer the structural information of that particular nucleus. So one of the major tools to study nuclear structure is via nuclear reactions. Third important reason that why we need nuclear reaction is to probe the dynamical characteristics of nuclei and nuclear matter. What does this mean? This means that suppose in the oxygen 18, suppose oxygen 18 is basically reacting also, for example, oxygen 14 is reacting with alpha particle. Now we want to understand that oxygen 14 and alpha particle are basically reacting with some energy, and then something will happen in the nuclear reaction. So during that happening, neutrons and protons basically in the two nuclei make rearrangement, and for that rearrangement, what sort of things can be observed? Those things basically are called the dynamical characteristics. So if we want to study the dynamical characteristics of nuclei, then we need to have some nuclear reactions. Nuclear reaction energetics. In this slide also, we are continuing our discussion about the energy in the nuclear reaction. The minimum kinetic energy that the projectile must have to make the reaction go is called the threshold energy of the reaction. So it should be understood by now that to initiate any reaction, there is always a minimum energy requirement as per the conservation laws. So as per the conservation laws, whatever minimum energy is required to initiate a reaction, that energy is called the threshold energy, and this threshold energy must be satisfied. For 108 lead, 7 lithium, 215 astatine reaction, Q is equal to delta 208 lead plus delta 7 lithium minus delta 215 astatine minus delta gamma. So when we solve their values, we get Q is equal to minus 5.589 MeV, and since the sign is negative, it shows that the reaction is endothermic. Nuclear reactions barriers. Now in the previous slide, we have understood that to start a reaction or to have a reaction, to have a nuclear reaction, there is a minimum energy requirement that must be satisfied. Now even if that energy is there in the reaction, reaction may not follow, or you may not have the nuclei reacting. Why it is so? The reason we will understand in this particular slide. Now in the nuclear reaction, we have two nuclei which are positively charged. So when the two charged nuclei are coming close together to react, there will be some electromagnetic interaction in the form of Coulomb force between the two nuclei will take place. Due to this electromagnetic interaction, the nuclei will hesitate to come close together to do the nuclear reaction. So we need to overcome this barrier. This barrier is called Coulomb barrier. We need to overcome this barrier in order to have a nuclear reaction. So this is another condition. One condition is of threshold energy. Another energy condition is posed by the Coulomb barrier. So failure to observe nuclear reaction at bombarding energy E beam is equal to E threshold. Even though energy and momentum are conserved is due to the repulsion between two positively charged nuclei. Now here in the picture on the right hand side, it is clearly shown that due to the Coulomb barrier, there is a potential hike which the projectile has to surpass. It means the energy of the projectile has to be more than the Coulomb barrier to make the two nuclei come close together and have reaction. This Coulomb barrier can be obtained or can be calculated using the simple Coulomb energy formula, like Coulomb potential is equal to 1 by 4 pi epsilon 0 Q1 Q2 over R. When we incorporate the values of Q1 and Q2 and value of R, we obtain the relation as V Coulomb in the center of mass frame is equal to 0.90 Zp Zt over AP to the power 1 by 3 plus AT to the power 1 by 3 MeV. So this is the expression for Coulomb barrier in the center of mass frame. But experiments are done in the lab frame. So we need to know how much energy of the projectile is needed to have a nuclear reaction. So we need to convert this center of mass energy into lab energy to get the proper idea of when the reaction can happen. So to do so, that is to obtain the Coulomb energy in the lab frame, we use this formula, like V Coulomb lab is equal to ACN over AT V Coulomb center of mass, where ACN is the total mass of the system, that is A of the compound nucleus upon A of the target. Nuclear reactions, barriers. So putting the values of Zp and Zt, which are nothing but the atomic number of the target and the projectile nuclei, and the values of AP and AT, which are nothing but the atomic mass of projectile and the target, we can find out the Coulomb barrier in the center of mass frame as well as in the lab frame. So once we know the value of Coulomb barrier, we are sure that we need to have energy more than the Coulomb barrier to observe the nuclear reaction. So conclusion is that the Coulomb barrier imposes another restriction on the nuclear reaction. Another means the first reaction was posed by the threshold energy. So Coulomb barrier is on the top of that. So Coulomb barrier imposes another restriction on the reaction energies. Just as alpha particles must penetrate the Coulomb barrier to escape the attractive nuclear potential, the same barrier inhibits charged particle entering the region of the nuclear attraction. For a nuclear reaction to happen, the supplied energy has to be greater than the Coulomb barrier, that is VCB. Nuclear reactions, energetics. Energetic means we want to study or we will study the energy involved in the nuclear reaction. We have seen that nuclear reactions happen and some energy is involved, whether the energy has to be supplied or whether the energy is released in the nuclear reaction. So that energy is called the energy of the reaction or the Q value of the reaction. If Q is positive, that is Q is greater than 0, such reactions are called exorgic reactions and they may produce spontaneously. What does that mean? That means these equations can produce by themselves and in an efficient way they can basically be proceed. Number second, if Q is negative, that is energy of the reaction is negative or Q is less than 0, such reactions are called endorgic reactions. In order to proceed those reactions, energy must be added before the reaction can occur. So it means they need energy to proceed. In the third case, when Q is equal to 0, Q is equal to 0 means no energy is released. So energy is involved, but no energy is released in the form of radiation. So in that case, we can say that whatever energy of the reactant is there, that energy is basically taken in the form of kinetic energy by the product nuclei. So in this case, recoiling will be there, but no excitation of the product nucleus will take place. So if Q is equal to 0, These reactions are called elastic reactions. No energy transfer to the product nucleus. Necessary condition for the occurrence of a reaction is Q plus Tp is greater than 0. So this is a general requirement for any nuclear reaction to happen, that mod of Q plus Tp should be greater than 0. What is Tp? Tp is the kinetic energy of the particle of the product particle emitting out. When Q is less than 0, the minimum kinetic energy needed is Tp is greater than equal to Q Mp plus Mt bracket close upon Mt. So it means when in case of endogenic reactions, when we need to supply energy, so how much energy should be supplied is given by Tp is greater than equal to minus Q Mp plus Mt over Mt. Coulomb nuclear reactions barriers. Now, what is the meaning of barrier? We have learned up to the previous slide that some energy has to get involved in the nuclear reaction. So it means energy must be supplied to carry out some certain nuclear reactions. Now, this energy requirement, what we are talking about to have a nuclear reaction, that energy requirement comes from the conservation of energy, conservation of angular momentum. But it is seen that even if that minimum energy requirement is satisfied, even then the nuclear reaction doesn't happen. Why it is so? It is because in order to have the nuclear reaction, there are some more barriers, or there are some more energy requirement to overcome certain things. Those certain things are called barriers. Why that barrier things are there, and why they are so important? We can see here, one of the important barrier that two nuclei should overcome is the centrifugal barrier. What is that centrifugal barrier? It is an additional barrier that must be considered if angular momentum is imparted to the target nucleus. The rotational energy of a nucleus is given by E rotational is equal to L into L plus 1 h bar square over 2I. So this centrifugal barrier basically we can calculate, and the centrifugal barrier has to overcome. And in order to overcome the centrifugal barrier, we need some extra energy. When the orbital angular momentum L is equal to m into v, mv into b, and I is equal to mu r square, where mu is the reduced mass of the system, as L is equal to mvb can be 0, so it's not a minimum condition for reaction. So it's not a minimum condition to overcome the barrier, is not a minimum condition. It's an additional energy requirement on the top of the threshold energy. So why it is so? Because even if L is equal to 0, even if the angular momentum is 0, so in that case the nuclear reaction can proceed. So it means the minimum amount of energy is the threshold energy, and this is an extra energy requirement for the nuclear reaction to happen. For most reactions, the Coulomb barrier is higher than the threshold energy, the exception being found among the light target nuclei. So in general, what we have understood up to now, that in addition to the minimum energy requirement for nuclear reactions, there are two more additional barriers which the two nuclei has to overcome, and therefore need energy to overcome them. Those two barriers are basically the Coulomb barrier and the centrifugal barrier. For most reactions, the Coulomb barrier is higher than the threshold energy, the exception being found among the light target nuclei. For neutrons, of course, there is no Coulomb barrier. Why there is no Coulomb barrier? Because neutrons are uncharged. So they don't have any charge. So there cannot be any Coulomb barrier. So for neutrons, of course, there is no Coulomb barrier, and the Q value are positive. So there is no minimum energy for most neutron-induced reactions. So students, let us summarize what we have learned in this module. Now we have came across a number of concepts in this module, but now we want to summarize that what we have gained, what we have achieved after going through this module. The first thing we learned is that nuclear reactions are important for a variety of reasons. So it means nuclear reactions are important. Second thing, for a given entrance channel, there can be various exit channels. So it means if the beam target, for the same beam target combination, different set of product nuclei are possible. Third thing that we understood is, except in case of neutrons, there is minimum energy requirement for every nuclear reaction to start. So it means only the reactions involving neutrons can start by themselves, but other reactions, basically energy is required. In case of charged particles, the minimum energy limit is decided by the maximum among Coulomb barrier, centrifugal barrier and threshold. So this is very important, because we have seen that there is energy requirement, there is minimum energy requirement which is called the threshold energy for a reaction. There is also energy requirement for the Coulomb barrier to overcome the Coulomb barrier between the two nuclei reacting. And there is an additional barrier called centrifugal barrier that must be overcome and therefore need energy. So which one is the minimum energy that we will decide on the basis of their value. So the rule is that maximum among Coulomb barrier, centrifugal barrier and threshold value will be the minimum energy required for that particular reaction.